Welcome to my class. Today I will start with the topic crystallography. Let me write first. First, let us understand why we will study crystallography or what is crystallography and why we need to study about crystallography. Crystallography is the science which deals about the arrangement of crystal structure. Now, what is a crystal structure? A crystal structure is a solid structure where the atoms or ions or the molecules are arranged in a periodic way. So, you may think that why we will study crystal structure or what is the necessity to study about the crystallography. Many physical properties or the optical properties, then thermodynamic property, all these properties depend on the crystal structure. So before we start to understand the crystal structure, we should know about the basic things of the crystal structure. So first thing is about space lattice point, which is space lattice. Now, what is space lattice? It is actually a symbolic language for a crystal structure. Space lattice is, let me draw first. Space lattice is, obviously here as it is 2D, so I have drawn here in 2D. It is actually a 3-dimensional, in reality it is 3-dimensional. So space lattice or lattice points is 3-dimensional arrangement of points, and let you are standing at this point A or you are standing at the point B. If you stand at the point A, the environment that you will observe is exactly same as when you will stand at the point B. So lattice, space lattice or lattice points is 3-dimensional arrangement infinite, and this is infinite obviously in all the directions and in front side also. Infinite arrangement of points in space where each point have identical environment. Now, if let us draw this line, let us join these 2 points AB. This AB is called translational lattice vector, which we denote by the symbol T, which we define as T is equal to N1A plus N2B. Now, what is N1, N2, AB? I will say. A, let along this direction, I take a parameter as A. Along this direction, I take a parameter B. These A, B, these are called lattice parameters, and N1, N2 are the any integer. So T translation vector is denoted by N1A plus N2B. Obviously, I have written this in 2 dimension. If it is in 3 dimension, then there will another term, that is N3C, where C will be lattice parameter along this direction. A is the lattice parameter along this direction, B is along this direction, C is outside from the board. Okay. This T is called the translation lattice vector. Next is basis. This is also called as motif also. Okay. Now, what is basis? In actual crystal structure, it is not consist of only the points. There may be ions, there may be molecules, there may be atoms. So, depending on the structure of the crystal, there may be one atom at each lattice point. Then it is called single basis atom, like copper, sodium. These are single basis atom. This is atom. If there are 2 atoms at each lattice point, then it is called diatomic basis. For example, sodium chloride, then cesium chloride, they are diatom bases. If there are 3 atoms are there, example you can write as calcium fluoride, it is triatomic basis. So depending on the structure of the crystal, it may be 1 or 2 or 3, many more. This group of atoms is called bases. So how a crystal structure is formed? When the basis is there is associated at every lattice point, then crystal structure is formed. So mathematically we can write lattice together with basis form the crystal structure. Okay. Let us come to the next point. Let us now understand what is a unit cell. What is a unit cell? Let me draw this picture again. The same picture, because it is now become clumsy, so I will redraw this picture. I will draw the lattice points in 2D. Let me draw one block. Let me draw this second block. And let me draw this third block. Let I name is at 1, 2 and 3. See, if I repeat this block 1 in all the direction along, let it take as x-axis, let it take as y-axis, and perpendicular to the plane of the board as z-axis. If I repeat this block in all the direction, I can construct the whole space lattice. Similarly, if I repeat this block 2 in all the directions, again I can construct the whole space lattice. Or if I repeat this block 3 in all the directions, again I can construct the whole space lattice. This block 1, 2, 3, these all are called unit cell. So what is a unit cell? I can call it as a basic building block by repetition of which in all the direction I can construct the whole space lattice. That is the unit cell. Then now see what is the difference between this 1, 2 and 3. See, in block 1 the lattice points are only at the corners of the cell. In block 2 the lattice points are at the corners of the block. But in block 3 the lattice points are at the corners of the block, as well as there is another point at the center of the block. This one is called primitive cell, and this 3 is called as non-primitive cell. So what is a primitive cell and what is a non-primitive cell? A primitive cell is a unit cell where the lattice points resides only at the corners of the block. And in non-primitive cell, the lattice points are at the corners of the block, as well as there may be another lattice point at any other position of the block. Obviously that there should be symmetry. So that is primitive cell and non-primitive cell. So we can say that all the primitive cells are unit cells, but all the unit cells are not primitive cells, because in primitive cell their lattice points will be only at the corners, and in the non-primitive cell the lattice points will be at the corners as well as center. So both the primitive and non-primitive are unit, but this non-primitive is not, we cannot call that non-primitive as a primitive cell. So all the primitive cells are unit cells, but all the unit cells are not the primitive cells. Okay. So next is concept of Bravais lattice. Bravais lattice. First, the French scientist, he is Auguste Bravais. He is a very famous French scientist, and his work in the field of crystallography is very useful. He first showed that in 3 dimension there can be 14 types of arrangements are possible in 3 dimension. So there may be 14 types of Bravais lattices are there, which are categorized in 7 type of crystal structure. The 7 type of crystal structures are, I will read out the name from the table. You can see the table. In the table, you can see the names of the crystal structure. These are triclinic, monoclinic, orthorhombic, cubic, tetragonal, trigonal and hexagonal. Now, how these crystal structures can be categorized? See, as before I have said you that this is let A, this is B, and let perpendicular to the plane of the board is C. This A, B, C were lattice vectors. Normally we take A along x-axis, B along y-axis and C along z-axis. This x, y, z, these are called crystallographic axes. This A, B, C are called lattice parameters. The angle opposite to A, let I have denoted it by alpha. Angle opposite to B, let I have denoted it by beta. The angle opposite to C, let I have denoted it by gamma. As A, B, C, these are called A, B, C. These are called lattice vectors. These alpha, beta, gamma, these are called interfacial angles. Together this lattice vector and interfacial angle, they together is termed as lattice parameters. So depending on the values of the lattice parameters, that is what is the relation between A, B, C and alpha, beta, gamma, we categorize this crystal structure. See, for triclinic, the lattice parameters A not is equal to B, not is equal to C, alpha not is equal to beta, not is equal to gamma, not is equal to 90 degree. You can see for monoclinic, A not is equal to B, not is equal to C, alpha is equal to gamma is equal to 90 but not is equal to beta. For orthorhombic, A not is equal to B, not is equal to C, alpha equal to beta is equal to gamma equal to 90. This cubic structure, which you are also familiar with, A equal to B equal to C and alpha equal to beta equal to gamma equal to 90. For tetragonal, A equal to B but not equal to C and alpha equal to beta equal to gamma equal to 90 degree. For trigonal, A equal to B equal to C, alpha equal to beta equal to gamma, but they are not equal to 90 degree. For hexagonal, A equal to B equal to not equal to C, alpha beta 90 but gamma equal to 120 degree. So depending on the value of these A, B, C and alpha beta gamma, we categorize the crystal structure. And again you see that for triclinic, see, the Bravais lattice is simple. That means it is primitive. So let us now draw three types of structure. Simple, one is simple, where the atoms resides only at the corners of the block, which is also called as primitive. Next is body centered. That means there are atoms at the corners of the cube, corners of the block, and one is at the center of the block. This is called simple. This is called body centered. One is face centered. Now as I am drawing this diagram on a board, so you may think that there is no difference of body centered and face centered. See, if I draw a cube, let I am drawing a cube. So body centered means one atom will be at the center of the body. That means at the center of this body. Face centered. So the name indicates that along with the atoms at the corners of the block, there will be one atom at the center of each face. So if I draw a cube, so along with each corner, there will be one atom at each face of the. So 1, 2, 3, 4, 5 and this is 6. As for a block, there will be, for a cube, there will be 6 faces. So there will be 6 atoms at each center of each face. This is called face centered. Another is base centered. Base centered is along with the atoms at the corners of the block, there will be one atom and one atom in the top, one atom at the bottom of each block. So it may be on these two sides, it may be on these two sides, or it may be in the front and back side of the cube. This is called base centered. Okay. Now Bravais, how categorize the crystal structure? You see, for triclinic, the Bravais lattice structure is simple. That means it has the atoms only at the corners of the cube. Okay. Then for monoclinic, you see the Bravais lattice are two. One is simple, one is base centered. That means one is simple. That means in this case, only the atoms will be at the corners of the. Let me draw it also as 3 dimension. At the corners of the block, and base centered means the atoms will be at the corners as well as any two parallel face, at the center of any two parallel face. For orthorhombic, the Bravais lattice are 4. Simple, base centered, body centered, face centered. So here the possible structures are the simple, body centered where the another atom is at the center of the body, face centered that means center of each face, and base centered that means center of any parallel faces. So there are 4 types of Bravais lattice. Cubic is simple, body centered, face centered. So these first 3 for cubic structures. For tetragonal, the structures are simple and body centered. That means these first 2 simple and body centered. Then for trigonal, again it is simple. For hexagonal, again it is simple. So now you see, for triclinic 1, for monoclinic 2, for orthorhombic 4, cubic 3, tetragonal 2, trigonal 1 and hexagonal 1. If you add all these, you will get the total number as 14. In this way, Bravais had shown that there are total number of lattice in which it can be arranged is 14, and this 14 Bravais lattice can be categorized into this 7 crystal structure. This is the concept of Bravais lattice.